Hello, everyone, and welcome to the lecture on global climate change. We're going to talk both about the contribution of sort of human-driven climate change over the last century or so, based on the kind of industrial revolution and the release of large amounts of carbon into the atmosphere as we industrialized. But we'll also talk about global climate change in the geologic record, as climate change is a natural process. CO2 and other greenhouse gases are emitted by both human activity and also natural processes. So the Earth has undergone multiple events of climate change, and we're going to talk about some of the evidence for that and some of the effects of that and how we might mitigate future weather events and catastrophe based on human-driven climate change. So we'll start with a global climate assessment from the National Oceanic and Atmospheric Administration, also known as NOAA, which is a government organization that tracks these things. And this is a 2021 report that they put out, and some highlights from that is that, yes, we are indeed warming faster. The Earth's temperature has risen about 0.14 degrees Fahrenheit, or about 0.1 degrees Celsius, per decade since 1880, which was the beginning of the Industrial Revolution, sort of en masse, in Europe and the US. And the rate of warming has more than doubled since 1981. And we keep breaking records. So 2021 was the 6th warmest year on record based on NOAA's temperature data. The 9 years through 2013 to 2021 rank among the 10 warmest years on record. Now, that doesn't mean the warmest years ever in the history of the Earth, just since we've been measuring it. And as of today, July 2023 is the hottest month ever recorded on Earth, and that's a global average temperature. And the way they measured this average temperature globally, they kind of just zeroed in on one spot in the northeastern Atlantic, bordering western or northwestern Africa and southwestern Europe in the Atlantic there. And they're measuring daily sea surface temperatures. And you can see throughout the 1970s, 1980s, things tended to be below average, average being this 0 line here. And in the 90s, it started to creep up. In the 2000s, creeping up even more into these orange and red colors. The 2020s are definitely hotter than the 2010s, though the 2010s were setting records. And this black line here is this year so far. And you can see this pretty incredible jump to about 1.5, 1.55 degrees Celsius above global average. And so you can see here in July, we reached a peak, and the temperature has gone down slightly, but keep in mind we're still a degree above. And I remember when climate change was being discussed maybe 10, 15 years ago, 1 degree Celsius was supposed to be the point of no return, and you can see we've almost doubled that. Here is another way to put that. So here's the 1880s. So this would be the beginning of the Industrial Revolution. Temperatures were still below average for the most part. So we were pumping CO2 into the atmosphere, but it wasn't having any real recognizable changes, though it might, which we'll talk about when we come to sort of negative feedback loops later on. But then about World War II, we see a huge spike in average global temperatures. Then in the post-war, we see temperatures kind of drop back down again. And remember, there's a lot of nuclear testing happening right through here. And then through the early 60s, with the rise of more industry and automation and sort of prolific use of automobiles, we see even more increase here. But what's notable is this trend here. So once we hit about 1980, temperatures stay above average, and while there is some fluctuation up and down, the overall trend line is increasing. And in the kind of late 2010s, mid to late 2010s, we start to see really high spikes, almost up to 2 degrees Fahrenheit. So from that same 2021 NOAA report, they have this graphic. I won't read through all of these, but I'll point out a few of the kind of major takeaways from this figure. What we see along the equator here, generally we'll see more rainy seasons in certain times of the year. So central Brazil had 91 days of record rainfall, causing the Amazon and its tributaries to flood. This was a once-in-a-century flood. This was in 2012. East Africa saw failed rainy seasons, resulting in one of the worst droughts in 35 years, causing food insecurity for about 20 million people in East Africa. We see an uptick in hurricanes in the 2010s. Some of you may remember Hurricane Ida, Hurricane Grace, one of the strongest hurricanes ever to make landfall. We've also had subsequent hurricanes. I don't know if you remember Galveston, Texas getting kind of obliterated, and parts of, I think it was Houston. And we see sea ice extent in the Antarctic dropping. The sea ice has a cycle where it expands out in the winter away from the continent and moves back towards the continent in the summer. And so that extent is dropping, similar to what we talked about with glaciers. If a glacier is melting, all the ice is still moving in one direction. Similarly here, ice is still moving out away from the continent down by Antarctica, but the extent to which the ice extends in the winter is dropping, and the same is true of Greenland. So we're getting net melting of the ice caps on the North and South Pole. And then if you look through this figure, just a lot more extreme weather events, and global average temperatures are warming as well. So what does this have to do with geology? Well, the climate system is multidimensional, right? It's complex and has a lot of interacting parts. And the parts that are interacting with climate are the very spheres, if you will, that geology is concerned with. So remember, geology is the study of Earth systems as a whole, and that includes the atmosphere, hydrosphere, geosphere, which is the rock cycle, the biosphere, and the cryosphere, so ice and snow cycles. And if we look at that, an increase in global temperature will affect the atmosphere and the hydrosphere, and therefore the biosphere, right? What plants grow where people live, damages to life just in general, or effects on life, and the cryosphere as well. So an increase in global average temperatures is going to affect the way glaciers behave on the surface, whether they melt or whether they advance. So in times of global cooling, you'll get more glaciation, and in times of global warming, you'll get less glaciation, and that means there's more water freed up to go into the oceans. And we'll talk a little bit about what that means when more of the Earth is covered by ocean versus continents. And the geosphere affects this, as I mentioned earlier, in the fact that natural processes like igneous activity, so volcanoes, things like that, will contribute certain atmospheric gases that will affect the way heat is stored and distributed around the planet. So the geosphere can affect this as well and be affected by it as well. And overall, a very dynamic and complex situation that incorporates all the different aspects that earth science and geology specifically are concerned with. So for climate, the geology connections are the climate impacts many geological processes. So remember, geologic processes aren't just the rock cycle, but also weathering, flooding, and mass wasting. So how much is stuff being eroded? How much is that stuff being transferred? And geologic processes also affect the climate. So you can have volcanism and mountain building. So with volcanism, we're releasing gases into the atmosphere. Maybe not at the same rate that we release gases into the atmosphere through human influence, but still significant and enough to affect climate in the geologic past. And then also you have mountain building. Sometimes when you have mountain building, you get certain chemicals being sequestered from the atmosphere as that process happens. And we can talk about that in the discussions if you want, and if you have any questions about how that happens, I'm happy to explain it. But basically, you know, when you have mountain building, you have metamorphism, and when you have metamorphism, you have the recrystallization of new minerals, and sometimes that will pull certain elements out of the atmosphere to build those minerals, and that's just a chemical process that happens. So geologic processes can contribute and take away chemicals from the atmosphere. So how do we detect climate change? Well, for climate change in the geologic past, we do something called paleoclimatology, and that's reconstructing past climate data using something called proxy data. And proxy data can be defined as indirect evidence of climate change. So how is climate change detected? By using proxy data. Well, you can see these two gentlemen over here are auguring into the sea ice, probably in Greenland, possibly in Antarctica. And some things that we look for when we're taking ice cores like this is we're looking for the evidence of seafloor sediment, which we can do through deep sea drilling as well. And they're sort of a storehouse of climate data. We also look at oxygen isotope analysis, namely through oxygen 16, which is the stable isotope of oxygen. That's going to be oxygen with the requisite number of protons and neutrons to be stable. Sometimes you might have 2 extra neutrons. So it's still oxygen because it has the same number of protons, but it has more neutrons, so it's what we call heavy oxygen or oxygen 18. And during times of, excuse me, during times of warming and during times of cooling, there's more or less oxygen 18 in the atmosphere. And I have a slide on that, so we'll talk about that. Climate change can be recorded in glacial ice. This can be those same oxygen isotopes as well, but also certain other trace gases and sometimes pollen and things like that can tell us whether the planet was warmer or cooler at a certain layer in the ice, and that correlates to a certain time in the Earth's history. Believe it or not, we look at tree rings. So tree rings can be archives of environmental history in the fact that in a year of lots of precipitation and sufficient heat in the summer, you'll get thicker tree rings than you do in times when there's more drought and the trees being more conservative and not growing as much. And so we can look at things like that. And then I've mentioned some of these other types of proxy data, but we've got fossilized pollen, corals, and sometimes we even use historical data. So, you know, a history book from the 700s in Iceland talks about a giant eruption. We say, okay, that's great. Let's try to verify it. So we'll try to correlate that with ice cores from that time period and see if we see an increase in CO2, a decrease in certain other gases related to volcanism, etc. So for seafloor sediments, being a storehouse of climate data, basically here we're looking at the abundance and the types of organic remains that we see in the fossilized record. So seafloor sediments are made of tiny plankton shells. Tiny plankton shells are made of silicates, or they can be made of calcium carbonate. And the amount of calcium carbonate available in the dissolved ocean water, that is, if there's more CO2 in the ocean water, that means there was probably more CO2 in the atmosphere at the time, right? Because it was available to be dissolved in the ocean. That's going to give these little planktons a lot of opportunity to grow more shells, okay? Because there's more CO2 available in seawater to build those structures. And so the abundance of lots of calcium carbonate shelled organisms, or the relative scarcity of these, tell us something about how much carbon was in the system, i.e. the atmosphere or the ocean at the time of formation. So if we're looking at oxygen isotopes, to also sort of correlate times of global cooling versus times of global warming, it's important to notice that during times of global warming, we have high sea level, right? And so there's more oxygen 16 and more oxygen 18 dissolved in water. And so the ratio between the two is about even, so it stays at about 0. But once we get global cooling, more water is being sequestered in glaciers or held up in glaciers, and we have lower sea level at that point. But you're still getting evaporation during times of global cooling, but oxygen 16 is preferentially being evaporated, okay, even during times of global cooling. So we tend to see in the lower sea level more oxygen 16 evaporating, and so you have a higher ratio of oxygen 18 to oxygen 16, and in this case, about 1%. And these ratios can be recorded in the calcium carbonate shells, remember, because a carbonate is a carbon and 3 oxygen atoms bonded to that carbon. And so some of those oxygen atoms will be made of oxygen 18 rather than oxygen 16, since most of the oxygen 16 has evaporated and precipitated onto the glaciers as snowfall. So we can look at the ratio of 18 to 16 in all sorts of marine organisms, and we can decide then whether we're looking at a time of high sea level or global warming, which is an interglacial period, or a glacial period where we have lower sea levels and global cooling. We also use glacial ice cores, so climate change can be recorded in glacial ice. We can go back about 200,000 years of climate history in the Arctic, and that's because the ice there is a little more unstable and is more subject to melting and thawing, and so it's not preserved as long. But in the Antarctic, there's ice there that's been on that continent for about 2.7 million years. And so all the data is trapped in that ice, and the further down you drill and get these ice cores out, like you see over here on the right, we can analyze those ice cores from those big depths and get some climate data from, millions of years ago. And the ice is analyzed for oxygen isotopes, like I mentioned in the previous slide, but also the amount of carbon dioxide or methane trapped in air bubbles. So atmospheric air can be incorporated into the ice through air bubbles, and that is a closed system, so there's no gas moving in and out of those bubbles. They're locked in the ice. And so we can take really careful and precise measurements of carbon dioxide and methane concentrations in that atmospheric air that's trapped in those bubbles, along with dust, volcanic ash, and pollen. And we have instruments that are sensitive enough to read those amounts and can tell us something about whether there was more greenhouse gas present in the air bubbles. And if we see signs of global warming, we can correlate that with how much dust we see or lack of dust we see, how much volcanic ash or lack of that we see in the bubbles, and how much pollen. So what types of plants were growing around the equator and further from the equator during times of global warming or global cooling. And then again, I mentioned tree rings, so they're archives of environmental history. So growth rings are added annually, and the thickness and density of the rings reflect the environmental conditions. So Ring chronologies can extend back thousands of years if you have trees that are that old, and we do. And here you can see a variation in the thickness of these tree rings. And this is going to be a summer in the light brown and tan here, and then the winter is this kind of darker color when the tree is thickening up its bark and protecting itself while it's dormant in the winter. And we'll see thicker rings in times when the climate was a little bit warmer and there was more precipitation, and thinner rings when there was less precipitation. And then also, again, we have the proxy data of fossilized pollen, corals, and for fossilized pollen, we can get lake sediments, and they can give us regional vegetation. And regional vegetation that was present during the time of formation is very much climate dependent, and that should make sense. And then we also have oxygen isotopes in coral analysis, and corals are a really great feature for studying climate change. We call them paleothermometers because corals are very sensitive to changes in ocean temperature, very sensitive to changes in ocean chemistry. So in times of warming, when more CO2 is being dissolved in the ocean, you get a slightly higher acidity, and that acidity, or those more acidic conditions, can affect corals in ways that we can measure. And that'll tell us something about the dissolved gases in the ocean and therefore climate. And then we also have historical data, like I mentioned. So what we can do with all of this proxy data is we can try to line it all up and correlate it based on the times that we're measuring. And we can try to put that all together and see if oxygen isotopes suggest warming or cooling during a certain time period, and does that line up with what fossilized pollen suggests or what seafloor sediments suggest, etc. And when we do that, we see that there were times of above average temperatures, times of below average temperatures, and then some uncertainty we always include in science. We like to, in any graph, we'll include how uncertain we are in the fact that, let's say here in the beginning of this graph, we've got maybe 0.25 degrees Fahrenheit above average, but based on the way we measured it and the way we calculated it and some of the suggestions from other proxy data, it could be as high as 0.75, for example, or as low as 0.75 in that area. So uncertainty keeps us honest and makes sure we're not making assertions that we can't prove. But during the advent of the thermometer, and when we started keeping thermometer-based records, we can see that since about the late 1800s to the present, we are experiencing globally much higher temperatures than we have in the past 1700 years. There were periods of warming during the medieval times. This is actually what allowed some of the sea ice to melt up in Scandinavia, allowing the Vikings to kind of break free of their little sequestered area in Northern Europe and travel around wreaking all kinds of havoc. So this was during the medieval warming period. And so this is an example of where we have historical data from Europe of Viking invasions in England and France and even as far south as the Middle East. And that correlates with climate data that we see in oxygen isotope data, tree ring data, etc., showing that, yes, there was indeed this kind of medieval warming period, and that kind of all lines up. So that's a good example of historical data being compared to sort of more scientific proxy data. And then also we had a little bit of an ice age during the 1600s to about the 1900s, where we had lower than average temperatures, and we can correlate that using all the proxy data we've talked about. And then with thermometer data, now we have actually true, global average temperatures recorded, and we see this big spike here during the Industrial Revolution and kind of the industrial influences of the 1900s. So when it comes to the atmosphere, let's just talk about the atmosphere really quick. What's it made out of? So the composition of a clean, so not contaminated, and dry, so not too much water in the form of clouds, is usually a mixture of discrete gases. So it's mostly nitrogen and oxygen. It's almost 80% nitrogen, 78% nitrogen, and 21% or so oxygen. Carbon dioxide makes up about 0.04% of the atmosphere. An inert gas, which is a noble gas at the end of the periodic table there, it doesn't react with anything. Argon, that makes up about 0.1% of the atmosphere. And then there's concentrations in much smaller bits in parts per million of neon, helium, methane, krypton, and hydrogen. And then all other elements are basically too small to measure. So these are kind of the major elements that make up the real small percentages. So you can see it's mostly nitrogen and mostly oxygen. And even though this carbon dioxide here is a really small amount, about 0.04% of the overall atmosphere, it can still absorb a substantial amount of heat from solar radiation, i.e. the sun, and affect global climate. So what we add to the atmosphere, what can be added to the atmosphere, is water vapor, which makes up about 4% of the air at any given time, sort of average globally. It is the source of clouds and precipitation, and it absorbs heat and it can affect global climate. We have the ozone, which is it's an oxygen molecule that normally oxygen, when it's in the atmosphere, it bonds to another oxygen because oxygen is polar. It has a positive and negative polarity. And so generally, oxygen likes to bond up with one other oxygen, so we get O2. It's very rare that you'd see just a single oxygen atom floating around in the atmosphere. Generally, it makes O2, right? Because it's happy to be bonded to itself. We call these diatomic elements. But there's a thin layer concentrated in the upper stratosphere where you have 3 oxygens bonded together, and this is O3, we call it ozone. And this absorbs harmful UV radiation through a chemical process that you don't necessarily need to know. But basically, the O3 here is sort of unstable, and when it gets hit by UV rays, it breaks up into O2, and so it's absorbing that ultraviolet radiation, whereas O2, regular old oxygen, in the atmosphere does not. And then we also have aerosols, so tiny solid and liquid particles. They can attract moisture and they can seed cloud formation. And mainly they block sunlight from reaching the earth, right? So they create cloud formation. Cloud formation blocks sunlight. And so you can, I mean, this makes sense. Sunny days are hotter than cloudy days, usually. So the energy from the sun reaches us as electromagnetic radiation. So all sorts of things fall on the electromagnetic scale. Below visible light, you've got gamma rays and X-rays and ultraviolet rays. And above visible light, you've got infrared waves, microwaves, and then TV, shortwave radio, stuff like that. So electromagnetic radiation is a wave function. So it is a wave, and it reaches us as light or it reaches us as heat. And objects will absorb this radiation, and molecule movement increases, and so temperature increases. And I'll have more on that in a moment. The key difference between electromagnetic radiation is the size of the wavelength. So here you've got wavelengths in 0.001 millionths of a meter, also called a micrometer. 1/1000th of a meter, also it's called a millimeter. Then we've got 1 meter here, and then we've got 1,000 meters. So these wavelengths are really short, below visible light, and they tend to be the violets and blues. And then you have visible light, where we've got this spectrum here where we see violets, greens, and reds. And then above, you get kind of above red, that's infrared, and then microwaves, and these can have wavelengths of millimeters to kilometers. The basic laws governing radiation is that objects emit radiant heat. Hotter objects radiate more energy than colder ones. Hotter radiating bodies have shorter wavelengths here. And objects that are generally good at absorbing electromagnetic radiation are also very good at emitting it or releasing it back out. So when we're heating the atmosphere, let's follow a little packet of solar energy as it enters the atmosphere. So here's the sun emitting 100% of its radiation into the vacuum of space, and that hurls towards us at the speed of light. And when it reaches us, 50% of it gets blocked by the atmosphere. And so the other 50% hits the ground as direct or diffused radiation. And this is absorbed. So it reaches us as light and heat, and it's absorbed as heat on the surface on both land, so continental crust, and in the ocean, in oceanic crust and ocean water. 5% of it is backscattered back into space by the atmosphere, so it's not absorbed, it just bounces right off the atmosphere and goes back out. 30% is lost to space by reflecting and scattering. 20% is reflected by clouds. 20% of the radiation is absorbed by clouds, and then 5% is reflected back from the land surface. And this stuff, this 30% here, is kind of an accumulation of all of this, that the radiation that's being reflected back, and that's just lost to the vacuum of space. And what we call this is planetary albedo. And something I want you to think about is a continent that's covered in ice versus a continent that's not covered in ice. Is that going to reflect more or less? So imagine a continent covered completely in ice, so it's white in color. Will that reflect more, or will it reflect less? Well, if you said it would reflect more, you're absolutely right. So you'll notice if you're in the summer, if you're walking across some blacktop versus a white sidewalk, the blacktop is much hotter than the white sidewalk. And that's because things that are white reflect light, i.e. heat, away. So a white sidewalk is reflecting solar radiation away from the sidewalk back up into the air. And so it's a little bit cooler to the touch than something that's darker in color. So a planet that's mostly ice is going to reflect heat away, and that's kind of a runaway effect. You have less heat reflecting, or you have more heat, I should say, reflecting off of the surface of the planet. And so the planet gets cooler. That cooling creates more ice. That ice covers more land, making the planet more white in color. And that process just repeats. Similarly, a planet that is warming is going to have melting ice, so more of the surface is going to be ocean. Ocean is darker than land. Ocean absorbs heat. That heat then stays in the system, in the atmosphere, and melts even more ice, and so on. And so a darker planet can create runaway greenhouse or runaway warming effects. So here's that greenhouse effect. And we're going to look at the moon that has no atmosphere. We're going to look at the Earth, which has, the atmosphere that we've talked about. And then we're going to look at Venus. And solar radiation passes through the atmosphere and heats the Earth, right, as we see here. The Earth will emit long-wave radiation, so that's absorbed by greenhouse gases, for example, CO2 and water vapor in the atmosphere. That long-wave radiation heats the atmosphere, and while some escapes to space, a lot of it is redirected back to the Earth. So in this middle picture here, well, actually, let's start with the moon. So if the sun hits the moon, it reflects back as long-wave radiation. There's no atmosphere to capture it, and so it just hits the moon and then reflects back into the vacuum of space, and that's that. So there's no trapping of that heat at all. So on the light side of the moon, it's usually always hot on the surface because it's being hit by solar radiation. And even though that's reflecting back, if you were standing on the surface, it would be pretty warm. And if you're on the dark side of the moon, no solar radiation is hitting that, so the surface would be very cold. We're lucky on the Earth in that we have an atmosphere that does trap some heat, but not all. And so times during the day when the sunlight is directly hitting the surface of the Earth in one hemisphere, a lot of that greenhouse gas is radiated out, but a lot of it is reflected back by the atmosphere, and it traps that heat and it bounces around. And that heat is moving across the planet. And so even when it's nighttime on one hemisphere, heat from the previous day has been trapped, and heat that's being trapped on this side is moving in the form of convective currents throughout the atmosphere. And so we have a nice system on the Earth in that global temperatures stay fairly stable from about 0 degrees Celsius or freezing to about 70 degrees Celsius or something like that, where it would be really hot, 70 or 80 degrees Celsius. And so we don't get too hot and we don't get too cold. We are in what they call the Goldilocks zone. If you have too thick of an atmosphere with lots of greenhouse gases, solar radiation comes in. Most of the outgoing long-wave radiation is absorbed by these greenhouse gases and then is re-radiated back down onto the surface. And as that happens, more gases are being produced as the planet heats. The atmosphere gets thicker and thicker and thicker. And so you have something like they have on Venus, which is a runaway greenhouse effect. Runaway greenhouse effect is when all the heat's coming in, not a lot's being radiated back out into space. All that heat is being trapped, and that affects the atmosphere, and it creates this kind of runaway effect where it just gets hotter and hotter and hotter and hotter. And eventually, it's so hot that many of the gases that would support life, like oxygen, are overcome by carbon dioxide and sulfur gas and things like that, and makes for a very inhospitable planet. And Venus is super duper hot. We sent an instrument there a decade or two ago, I think. It landed on the surface successfully, and it took about, I think, 1.5 minutes to 2 minutes of readings before all the equipment basically started to melt. So as the global climate average raises in temperature or lowers in temperature, that can have drastic effects on weather events. And I think this deserves a little bit of clarifying because a lot of people assume that if the overall global temperature is raising, we should see warmer summers, warmer winters. And so obviously we would expect more drought and wildfires and things like that, lack of precipitation in the summer, but we would also expect the winters to be warmer as well. And while globally that is the case as far as averages, what a rise in global temperature actually does is it just increases the severity of weather events. So in order to understand this, I'd like to introduce you to something maybe you've heard before. This is Newton's first law of thermodynamics. Most people understand it as energy cannot be created or destroyed, and that's true. But really what it says is that energy can be converted from one form to another with the interaction of heat, work, and internal energy. And the way I like to think about that is a pot of water. So if I have a pot of tepid room temperature water, the molecules are, they're happy, they're interacting with each other as a liquid, and they have a certain amount of energy in their system that allows them to stay sort of stable, not heating up, not cooling down, so staying very much a liquid. When you begin to add heat into that system, that heat can't be, you're not creating heat where there wasn't heat. You're just taking heat from one space, namely your stovetop, and you're putting it into the water. And in order for everything to be at equilibrium, that is temperatures, pressures, densities, all of that, when you add heat into this system, it begins to excite the molecules and they begin to do work. And that's in the form of this internal energy here. So internal to the water, energy is being added. Molecules are speeding up, and they're going to begin to act very excitedly and break the hydrogen bonds that made this water a liquid and form little water molecules in the form of gas molecules. And that's how we boil water. Similarly, the atmosphere, when you add heat into it, and here we'll talk about a mass of air, often called an air parcel. When you add thermal energy to it, it warms the air and it increases the air's internal energy. And so it's not like the whole planet is warming up, it's that the planet is getting more excited, right? So the atmosphere is getting more excitable, so you're going to get more movement of moisture, more movement of heat across the surface. It's just speeding up. It's acting more excited, just like this pot of water here. And what that does is it just changes how things are distributed. So here's a precipitation chart over here, or a map of global precipitation in the December, January, and February months of the year, where we see higher than average precipitation on the poles and lower than average precipitation in certain parts near the equator, basically above and below the equator. And then in the summer, we tend to see less precipitation around the equator, but that tends to go a little bit further north, okay? So basically what's happening is you're getting dry periods in the winter around the equator, north and south, and that is rising up. So what you're seeing here is lower than average and higher than average precipitation in places that we wouldn't normally see it, relative to where it normally would be, because this color chart here is lower than average precipitation and higher in the red or orange and higher in the green. Beige would be kind of business as usual, zero above or below the average, and we don't see a lot of that. We see those areas kind of being choked out. So we're getting higher precipitation and lower precipitation based on changes in global climate. And this is affected mostly by the trade winds, the westerlies, the easterlies, the way that heat and pressure are being affected across the globe. So what does this internal energy look like? And like I said, it's the distribution of temperature and moisture in the atmosphere. And what this does is it leads to an instability in the atmosphere, and it leads to more extreme weather events. So you could get more rainfall in areas where, just because the system is more excited and it's pushing rain in places that rain normally wouldn't be pushed kind of annually. And so we get more flooding based on that. We can get heat waves where heat is being pushed into areas that it wouldn't normally be otherwise, just because the atmosphere is more excited. You get more cloud cover and moisture being distributed in areas that normally would be very sunny in the summer, now are more cloudy. So they're cooler than normal and they're receiving less sunlight than normal. and that would affect crops. And remember, crops are part of the cycle. They're releasing carbon dioxide, or they're releasing oxygen and absorbing carbon dioxide. So more crops will affect the composition of the atmosphere, and less crops will affect the gas composition of the atmosphere. With less precipitation also comes drier conditions. With drier conditions, we get the prevalence of more wildfires. And then ocean temperatures and the amount of moisture over an ocean can affect the severity and frequency of hurricanes. So global climate might be rising, but what that means in the short term, the takeaway here is extreme weather events, because stuff is just moving around faster, okay? So it's just more unstable. So there's a lot of talk about what humans can do to control the amount of effect we have on the atmosphere. But nature also has ways of doing this. The Earth sort of naturally responds to variations in climate over geologic time. And we call these controls. These are the ways that the planet responds to and causes changes in atmospheric temperature, weather activity, etc. And these natural climate controls are orbital variations, so variations in the Earth's orbit around the sun. This in turn affects solar intensity, so how much solar radiation is hitting the Earth at any given time and in any given location. The effects of plate tectonics, which leads to the amount of dust, volcanic gases, aerosols, etc., that are in the atmosphere at any given time. And some of those are greenhouse gases. So let's break this down. So with orbital variation, we get the change in intensity of the sun. So this is a function of the angle at which the sun's rays hit the Earth. If they hit vertically, they're more intense, and this tends to be at the equator. And at areas of low angles, so the northern hemisphere in our winter, and the southern hemisphere in its winter, the sun is hitting at more of an angle, and so you get less intense heating at the poles. And then there's minor changes in the Earth's rotation and revolution around the sun. And this affects the angle at which the sun's rays strike the Earth and can therefore have an effect on the intensity of that electromagnetic radiation as it hits. So the Earth, as you know, is rotating around an axis. That axis is not straight up and down relative to the sun. It's actually tilted. And the tilt currently is about 23.5 degrees, but the tilt, we have an actual, what we call polar wobble that happens over time, where you can get even more tilt of about 1 degree from 23.5, or 1 degree less from 23.5 at 22.5, the minimum tilt. And this happens about every 41,000 years. You get this wobble back and forth. And this changes the angle at which the sun is hitting the northern hemisphere and the angle at which the sun is hitting the southern hemisphere, at any given time. And so these changes will affect how much radiation is being absorbed from the sun and being captured in the atmosphere. And this can affect global warming and global cooling. We can also have orbital variations in the shape of the orbit of the Earth around the sun. And this is a very simplified model here, in the fact that the Earth is never actually revolving around the sun in this kind of circular pattern, but it can be more circular or less circular over a given time period. The Earth revolves around the sun in more of an elliptical orbit, more like an oval, I guess you could think of. And at some times during the orbit, the Earth will be closer to the sun, and sometimes it'll be further away from the sun. But this elliptical orbit can become more or less circular over time. And this is the eccentricity of the orbit. And its cycle is about every 100,000 years. The Earth changes from more circular to more eccentric. And so during times when it's more elliptical or more eccentric, you'd get the Earth much closer to the sun certain times of the year and much further away from the sun other times of the year. And when it's more circular, it would be more uniform when it's over here as opposed to when it's over here. You'd get similar amounts of solar radiation in this more circular orbit than you would in this elliptical orbit. And then similar to what we had in the slide before last about tilt, not only does the tilt of the Earth change, but also we get something called precession. And this is not just the angle of the tilt, but also you can get a wobble similar to a top on a table. If you've ever spun a top on a table, it's spinning with the top being fairly stable, fairly up and down. But then as it slows down, you start to get the top sort of wobbling a little bit and in a circular pattern. And we call this axis precession. And the Earth is likely slowing down in, I mean, this happens over, universally slow timescales, but we do see a similar precession in the Earth's axis that we do in a top on a table, in that the tilt is changing, but also that pole is wobbling in a circular pattern. And this can affect the angle at which solar radiation hits the Earth. So I want to give you an example of what orbital variation might look like by giving you an example of what would happen if you had very little variation in the orbit. So you're in a more circular orbit around the sun, and the axis is tilted at a fairly stable tilt with not a lot of precession or wobble. What might that look like on the planet? So if you have low seasonal contrast, where everything's pretty uniform between summer and winter, and that is a fairly stable climate, these are optimal conditions for glaciation because they require lower seasonal contrast or more mild summers, basically, to increase the possibility of any kind of accumulated snowpack surviving. And this would allow more snow and ice to accumulate in the zone of accumulation, and that would cause the growth of an ice sheet at lower latitudes. And so what this means is during times of high glaciation, let's say the last global maximum or glacial maximum during the Pleistocene, which formed most of the features that we see here in the Midwest, and especially in the Great Lakes region when we had these giant ice lobes that we've talked about. This is because you had milder summers, so less melt, and even though you had probably milder winters as well, they were accumulating snow just how they normally would, but that snow is not melting as much in the summer, right? And so you would get more glaciation. When you add heat to the system, like we've talked about, now you're getting more intense summers, more melting, right? Because the average global temperature is higher. And so when there's more orbital variation and you get more solar radiation hitting the Earth at certain times of the year than other times, it just makes for a more unstable climate. You're going to get more melting, and so you're going to get less glaciation, and you might experience some of those runaway effects that I mentioned before. Another natural control on climate is solar intensity. So the sun is emitting electromagnetic energy in the form of heat and light, and we're lucky for it. But that can vary over time. Lucky for us, what happens with solar intensity is you'll get solar storms, you'll get magnetic storms, and things like that, that create more light and more heat. But these are fairly short cycles. They tend to last about 11 years. It'll reach this kind of maximum, and then it'll drop down during that time. So about every 11 years, you'll get an increase in solar intensity for a brief time. And this might be a little counterintuitive, but this is too short of a time scale to have much of an impact on climate, because the Earth, for one, has a magnetic field, so that protects us from a lot of these, solar storms and things like that. A lot of the plasma and stuff that's ejected from the sun, when it hits the Earth, the magnetic field deflects it. That's why we have the northern lights. It's deflecting it up towards the poles. That's why we have, when you see the northern lights, if you've ever been lucky enough to see them, I have not, you're seeing solar radiation being funneled up to magnetic north and magnetic south. And that what you're seeing there is plasma interacting with the atmosphere just at the poles. And that's lucky for us, because that plasma is not interacting with the rest of the Earth, namely the part that we all live on, away from the poles. So thank God for the magnetic field. And because we have an atmosphere that is somewhat slow to respond to drastic changes in solar radiation, because we do live in that kind of Goldilocks zone. 11 years is not nearly enough time for the cycle of more intense to less intense solar radiation being able to affect us. So the Earth the atmosphere kind of normalizes the temperatures on the Earth in response to these much shorter increases and decreases in solar intensity. So lucky for us that is the case. Another natural climate control is plate tectonics. So tectonic changes between the different plates will create changes in elevation and the position of land masses on the Earth. So when the continents shift towards the polar regions, so higher latitudes, namely closer to the South Pole or closer to the North Pole, this can promote global cooling. Also, as you get more convergence amongst the continents, so say here during this supercontinent event here before the opening of the Tethys Sea, or after the closing of the Tethys Sea, depending, you'll get mountain building events. Mountain building events increases the elevation on land, and that's going to create more glaciation, because remember, glaciers like to form at higher latitudes. And remember, glaciers are land masses. So when the continents are at higher latitudes, there's more continental glaciation. And when continents are higher above sea level, there's more glaciation. Okay, and that promotes global cooling, because more glaciers means more ice. More ice means more white color on the surface, which reflects heat back. And so we would get a sort of runaway global cooling event. Whereas if the continents are spread apart and they're more focused around the equator, like they are today, we tend to get less glaciation because the continents are in a warmer zone on the Earth. That means a rise in sea level, so more dark coloring on the surface of the Earth. So that means absorbing more heat and creating more runaway global warming. So another natural climate control, as I've mentioned, is dust, aerosols, and volcanic gases being emitted into the atmosphere, usually through volcanic eruptions. And this increases the amount of dust and aerosol in the atmosphere. That scatters solar radiation, scatters it so it doesn't reach the surface, or reflects it back out into space. And this can cause global cooling. And sulfates are even better at this than water vapor and things like that. So when you get sulfates in the atmosphere, like particulates of sulfide minerals in the form of ash, you get even more reflecting and even more scattering of solar radiation in the atmosphere. And again, that promotes global cooling. And we can look at direct data from this. So right here on the y-axis, we have the net solar radiation percent change. And so we see this kind of annual solar radiation change from about 1970 or so. And then maybe a spike here and there, depending on whatever factors might have influenced that. But what's really interesting is then you have a big volcanic eruption here, and look at this drop in net solar radiation. So this is solar radiation being absorbed by the surface. When you have a large volcanic eruption, look, it dropped down 4% in 1983, and then similarly in 1991 or 1992, you had the Pinatubo eruption that released a lot of dust and volcanic gas into the atmosphere, and we see about a 3.4% drop in the amount of net solar radiation being absorbed at the surface. So volcanoes can have a huge effect on the amount of heat that's being absorbed into the system. And then briefly, I want to talk about oceans as being a natural climate control. So as you can imagine, currents will distribute different temperatures around the Earth, but also different temperatures around the Earth affect currents. So there is a bit of a feedback loop here when it comes to the way that the oceans distribute heat around the planet and therefore moisture and variations in pressure and weather and things like that. Currents affect this, and that's directly tied to temperature, but also something that people don't think about is volume. So if you heat the ocean up overall, you're going to get an increase in volume and a decrease in density based on that, because they are proportional to each other. So the ocean can kind of expand, and that can raise and lower sea levels, similarly to the way ice melting will raise and lower sea levels. And when sea level rises or falls, this has a big effect on the albedo, like I mentioned, of the Earth, and how much heat is being absorbed versus reflected back out into space or into the atmosphere. And so the oceans play a huge role in whether the planet is warming or whether the planet is cooling at any given time. And one of the final sort of natural climate controls is greenhouse gases. And we often think of humans as being responsible for the emission of most greenhouse gases that we see in the atmosphere today, and that's likely true. However, this also occurs naturally over scales of about maybe hundreds of years to even millions of years. And greenhouse gases, the kind of primary ones that we think about are carbon dioxide, obviously, as we've mentioned, but also methane, which is a carbon atom with 4 hydrogens attached to it. And the natural processes that reflect how much carbon or methane is in the atmosphere at any given time has a lot to do with weathering and fossilization. So when you have chemical weathering of rocks on the surface, a lot of times the carbon dioxide, or the methane in some cases, that is in the atmosphere will start to react with those rocks. That's the chemical weathering process. And as that happens, that carbon dioxide will be tied up in carbonate weathering. Okay, so if you weather a limestone, let's say that's a calcium carbonate, the water might split some of the calcium away from the carbonate molecule, and then that calcium is preferentially, as it moves through the weathering cycle, is going to start to bond through reactions with carbon dioxide in the atmosphere, pulling carbon dioxide out of the atmosphere. So that's one way that carbon dioxide can get incorporated into sediment, and we call that sequestering. But you can also get sequestration of carbon in rocks through the formation of fossil fuels. So any kind of organic material that's on the planet that's photosynthesizing, right? So plankton in the oceans and algae in the oceans, or surface plants in kind of swampy environments, that's going to pull CO2 into the biosphere, right? Because those things are breathing carbon dioxide and releasing oxygen. But once that plant dies, it's no longer breathing. So all of the carbon that's bound up in its biological structures gets buried and eventually becomes coal or oil or natural gas. So the carbon that's present in those fossil fuels is no longer part of the atmospheric cycle of carbon and oxygen. And so that carbon is being sequestered, right? It's being locked out of the process and it's being buried. So what we're doing when we burn fossil fuels is basically re-releasing that sequestered carbon into the atmosphere. But, and I'll talk more about that on this slide, on the next slide. But one thing I want you to think about is a reduction in carbon dioxide through this weathering process is going to create less greenhouse gases in the atmosphere, and those conditions do promote global cooling. So oftentimes after large events, like large weathering events, we tend to see global cooling. Although I will mention that this is kind of a perfect storm kind of a situation where you have to have a lot of factors coming together, geologically speaking, in order for large amounts of carbon dioxide and large amounts of methane to be sequestered. And this takes a long time, and things need to line up just right. So on the average, geologically speaking, natural global cooling events are fairly rare. Big ice ages are fairly rare. We've only had a handful of them on truly planetary scales over the history of the Earth. So let's talk about human impact on climate. So we do a number of things to impact the surface of the Earth. We might be the single largest biological influence on the planet thus far, with the exception of maybe those stromatolites that were creating most of the oxygen that we have in the atmosphere today. At during the Precambrian, they would have produced so much oxygen that they changed the composition of the atmosphere forever. So they had a huge effect too. But when it comes to modifying the land and modifying the atmosphere, we're number one as far as that goes. So for modifying the land, ground cover, basically plant life, has been cleared by us. We clear things when we log, we clear things when we create arable land for grazing and growing crops. And then also, we do controlled burns, or we don't do controlled burns and just let fires go unchecked. And this has a big effect on ground cover, which therefore has a big effect on levels of CO2 and methane and nitrogen and things like that in the atmosphere. Also overgrazing. So, we let a lot of our livestock overgraze. They're producing methane. There's no easy way to say this. Cows like to fart. That produces a lot of methane. That is a greenhouse gas. It does have an effect, believe it or not. And then overgrazing is also affecting ground cover. And this changes the reflectivity of solar radiation back into the atmosphere. It changes the rates at which water evaporates, right? Because ground cover tends to trap water, and less ground cover means more surface water evaporating out into the atmosphere, and that can have an effect on how much solar radiation is being reflected or absorbed. And this also changes surface winds. So how heat and moisture is being transported across the planet globally. And it modifies the atmosphere by adding greenhouse gases, that is CO2, into the atmosphere, mostly through the burning of fossil fuels and through deforestation. Burning fossil fuels takes that sequestered carbon that I talked about in the previous slide and re-releases it as a gas into the atmosphere, so that increases CO2. And deforestation is a decrease in surface plant life because we're deforesting, we're cutting all that stuff down, and it's not breathing CO2 and photosynthesizing and producing oxygen. So that would also lead to an increase in CO2 in the atmosphere. And we can see that in that CO2 levels are now the highest that they've been in the past 600,000 years. So if we jump back to 400,000 BCE or so, we're going to see carbon in parts per million being, as low as 180 to 170 parts per million. And for about the last 650,000 years, atmospheric CO2 didn't really rise much past this level. And we have this from ice cores and things like that. So we know that CO2 was never higher than about 300 parts per million. Starting at about 1950, we see a steep climb. And as of 2013, we've had an almost vertical rise to about 400 parts per million, and it is even higher today. So we see basically a direct impact of the last century and the industrialization of the last century and the amount of carbon in the atmosphere. And natural rises in carbon through different geological processes that I've just outlined never got past 300 because there are controls where the environment will respond to the amount of carbon naturally and some other process will take over and will keep these CO2 levels fairly steady. And that is not the case now. Here's another figure zooming in. So here's that same kind of cycle up and down of carbon, and here's that sudden rise above 400 at present day. And here's really what 1950 to 2021 looked like. So here we had about 310 parts per million, and now we're up at about 410 parts per million. The largest rise in the last 800,000 years happened in just the last 70 years. Global temperatures have increased as a result of more CO2. So global temperatures, as I mentioned, have raised about 0.8 degrees Celsius in the past century, and they're expected to increase. So the amount of increase really depends on the amount of emitted greenhouse gases, and we are doing more or less of that in certain parts of the world as far as how much CO2 we are emitting. So towards the end of the last century, we had zero amount of surface warming. In fact, we had negative surface warming to some extent because we were maybe entering into another glacial period. It's quite possible. But then about the end of the last century going into the 2000s and the aughts, this graph here is showing basically CO2 as a function of population growth and changes in global surface temperature based on CO2. So if we just held everything constant, right, no effect by humans at all, we do expect that we're entering a sort of warming period, but this is the CO2 emitted and the amount of global surface temperature rise stays below 1 degree. If there's low human growth, we still see, or population growth, I should say, we still see a rise in CO2 and a rise in global temperature. If we have moderate growth, shown here in green, we see a surface temperature of about 2.5 degrees. And if we have high growth, we can see, us skyrocketing up to 3 to 4 degrees Celsius rise. And then these lighter shades of these different colors are sort of the variation or the error between these models. So those people that make the argument that we're just in a natural cycle of CO2 rise and global climate rise, they're talking about this bar here. So this is, if we follow the cycles the way that we've followed them over the last 800,000 years, this is the amount of CO2 we would expect to see in the atmosphere and the resulting rise in temperature. We're seeing something quite different. We're probably more in this area here. So definitely human influenced. So I'll quickly talk about what an increase in temperature might mean. And we should talk about two different feedback mechanisms that are present as a result of warming. So we can have what you call a positive feedback mechanism. So this positive feedback is a reinforcement of the initial change. So if you have warming initially, a positive feedback mechanism would be increased warming. And an example of that is if we have warmer temperatures at the poles, we get sea ice melting. As sea ice melts, its high albedo white color on the surface is replaced by a lower albedo, darker colored ocean. This in turn increases solar radiation being absorbed at the Earth's surface into that darker color, so it raises the temperature of the oceans, and this increases surface temperature. And so we start with an increase in temperature and we end with an increase in temperature as the process continues. We also have negative feedback mechanisms. So let's say you start with warming, but the opposite thing happens. So this is a negative feedback mechanism. So this is a lot of times how the Earth would respond naturally through a negative feedback mechanism. So an example would be an increase in global temperature increases evaporation. An increase in evaporation increases cloud cover, which would reflect more solar radiation back into space and then lower global temperatures. So the Earth does this naturally oftentimes, and that would have been the increase in CO2 that we saw prior to the Industrial Revolution, where it increases moisture in the atmosphere and cloud cover, and then that will reflect more, and so that causes an eventual lower in global temperatures. But clouds can also have a positive feedback mechanism in that they absorb and emit radiation that might otherwise be lost to the troposphere, or lost out into the outer atmosphere and into space. So cloud cover kind of does both, but this example up here would be a negative feedback mechanism. So here we can talk about some possible consequences of global warming. And I'll say at the onset that the climate system, if you haven't gathered already, is very complex. It's a lot of different variables having effects on other variables. And the Earth system as a whole has many of these processes interacting with one another. And so predicting the exact consequences of global warming is really, really difficult. But some things that we might want to consider is that the magnitude of temperature increase is not globally uniform, as I've mentioned, right? The average temperature might be increasing, but if you zoom into any particular spot on the surface of the Earth, we're going to see the magnitude of that temperature increase varying. And so precipitation will vary across the globe. And so we're going to, as we see global average temperatures increase, we're going to see more rain in places that we didn't expect it, and we're going to see less rain in places where we did expect it, right? So, and that's just, again, part of that overall system getting heated up, and that heat is converted into internal energy and work. And here the work is pushing weather systems around, pushing currents around, pushing different temperatures around, and that's going to just affect how moisture and weather is distributed across the planet. And then also you can have a shutdown of previous ocean currents and the creation of new ocean currents, and that's going to cause cooling in places that we normally wouldn't expect it, and it's going to cause temperature increases in places that we wouldn't expect it, or it's going to make for areas that we know are going to be warm in the summer being even warmer, and areas that we know are going to be cold in the winter being even colder. So again, extreme weather events are definitely a consequence of global warming that we can accurately pinpoint. Other things that we can probably expect is from climate change is, in addition to extreme weather events, we're going to see sea level rise, most likely as glacial ice retreats. We're going to see a change in the Arctic as far as albedo, right? So we're going to see less ice cover at the poles, and that's going to change how much solar radiation is being reflected back. We're going to see changes in ocean acidity and others, probably some other consequences that I haven't even outlined here. There's going to be unintended consequences and unforeseen consequences as a result. But let's dive into a few of these. So for climate change, if we have higher maximum temperatures, we're going to also have higher minimum temperatures. But this is going to increase the frequency of heavy precipitation. So the likely outcome is going to be an increase in droughts and an increase in the intensity of hurricanes and cyclones. As far as sea level rise has risen about 0.25 meters, about a foot, or 25 centimeters since 1870. Sea level rise is driven by melting glaciers and also that thermal expansion of the water that I talked about. And I want you to think about where you think, where the impact would be greatest here. And I'll remind you that about 80% of the human population lives along the coasts of the various continents. And if you take my environmental geology course, one of the main things that we are going to talk about is the effects of coastal cities due to changes in the environment. But here is a graphic that shows a shoreline shift in areas where the slope is gentle. So think Eastern Carolinas, Virginia, places like that, and areas where the shoreline is much more rocky and mountainous, like we see in California and Canada, Western South America, places like that. So if you have a gradual shoreline, a rise in sea level is going to have a much larger effect than if you had a much steeper shoreline. Okay, so the east coast of the United States is in much larger trouble than the west coast, although cities like San Francisco and LA and San Diego, Seattle, maybe even Portland, even though that's on a river technically, can all be affected. But overall, the land isn't as affected as it would be on the East Coast due to sea level rise. We also have changes in sea ice at the poles, and I'm going to focus here on the Arctic, so the North Pole. Over here, you'll see there's the North Pole. And the amount of sea ice in any given year has declined about 13%, which is a lot, since 1979. So here we'll see 79, the extent of sea ice was at about 7.1 million square kilometers. And here we see the winter, summer, winter, summer, winter, summer, and so on through the decades from 1979 to now. And you can see, even though there's an up and down variation year to year, the overall trend is a decrease of about 13% in sea ice. And thawing permafrost is a positive feedback mechanism here. So as you melt the permafrost in North Asia, in Siberia, and in Alaska, and in parts of Greenland and Canada, there's more organic material being stored there, and that's releasing carbon dioxide and methane as it decomposes, mostly due to the fact that it's being exposed to the surface for the first time in thousands and thousands, maybe hundreds of thousands of years. So there's a lot of sequestered CO2 stored in the permafrost. So that's one of those unintended consequences that we don't necessarily foresee. But this is a really startling graphic, I think, in the fact that here's the median minimum, right? So this is summertime ice extent from 1979 to 2000. This is as far towards the pole as the ice has ever extended. In the winters, it would extend, down into land here more, but this is just sea ice. Here's the 2012 minimum. So much more ice is melting in the summer than it ever has before. And this is just 2012. It's actually worse now. We're 10 years past that, but I don't have that figure here. But as you can imagine, it's bad news bears. Possible consequences of global warming also are CO2 dissolving in seawater. This increases the acidity of the oceans. And here's a graph showing CO2 dissolved in the oceans at a station in Hawaii where they were measuring the pH of the ocean. And here we're seeing at the Mauna Loa atmospheric station, so measuring CO2 in the atmosphere, we see a rise from 315, 320 parts per million all the way up to 380, 385 parts per million. Okay, so that's atmospheric CO2 rising. But what we're also seeing is a rise in dissolved CO2 in seawater from about 325 parts per million up to about 8.3, 8.25 parts per million of dissolved CO2 in the ocean. And so the green here is showing you pH. So as there's an increase in CO2 in the ocean, we're getting a decrease in pH. And a decrease in pH is an increase in acidity. Now, I could throw a bunch of chemistry at you to show you how that's the case, but for our purposes in an intro class, we won't worry about that too much. But take our word for it. An increase in CO2 is a decrease in pH. A decrease in pH is a rise in acidity. And as ocean acidity increases, there's some real serious consequences for life. So it's harder for calcium secreting marine organisms to grow hard parts. We know this from our mineral and sedimentary rock IDs. When you add acid to a carbonate, it fizzes, right? It dissolves. And what does that dissolving do? Creates more CO2. So not only is it harder for calcite secreting marine organisms to grow those parts because it's more acidic, so it's harder to have stable calcium carbonate shells. They want to dissolve in that acidic ocean. But we also get coral bleaching, which is where calcium carbonate parts that are already there are starting to decrease and dissolve. And definitely click on this link in the slides and have a look at what that process looks like. But here is a bleached coral. So the previous slide showed a really robust coral colony with lots of life. Here's what happens when you increase the acidity of the ocean. So here we have bleached coral along a reef. Not a lot of life, and so not a lot of environment for plankton to form. That means hungry fish. Hungry fish means hungry bigger fish. And this is a collapse in the food chain, essentially, planet-wide. Plankton are the very first and foundational member of the global food chain. So not great. So if you ever wondered how a coral becomes bleached, a healthy coral has lots of algae, and they depend on each other to survive. So when you look at a coral, the coral is the actual hard part that you see, and then the algae lives in the spaces. A stressed coral, the algae leaves the coral and finds a different way to survive, leaving just the coral structures behind. So we call it bleaching. And that's just the calcium carbonate parts, no longer supporting any algal life. And so that's what makes it look bleached, is just that basically everybody moved out. So focusing primarily on the biosphere here, I want you to think about some of the other consequences. So much fanfare has been made about polar bears and how climate change affects them. And rightfully so, because they are sort of a microcosm or a sort of test case for the types of things that happen. Mostly, let's think here about food availability and migration. So as sea ice collapses, polar bears are not able to travel as far into the sea to feed on the things that they tend to feed on, namely fish and seals and things like that, because they can't travel farther enough out on the ice shelf to get at some of these things. So they're sequestered more towards land, and polar bears, their diet is only fractionally dependent on the types of things that they find on land. So so they're experiencing a bit of a famine, and also they're not able to travel as far, so their migration is affected. So famine, also disease. If they're packed into tighter areas, there's more chance of disease affecting them, and also new species that are going to exploit the lack of sea ice and the warmer temperatures are going to invade these areas, and invasive species are a huge problem for any biological population. So I want you to think about how this might affect you personally. So how is climate change going to affect you personally here in the Mitten? So in the coming years, there's going to be a number of things that happen or have already begun to happen as a result of climate change in Michigan. For one, increased precipitation and therefore flood risk, more severe storms, and that's both in the winter and in the summer. More extreme heat, so hotter days above 95 in the summer, which we've already started to see, especially in July there. Decline in cold adapted tree species like the paper birch and the balsam fir, which has a huge effect on paper industry, and but also has an effect on the biosphere here in Michigan as far as plant and animal species that rely on these cold adapted tree species to survive. A greater increase in algal blooms, which we're seeing in Lake Erie now, but we could expect to see them more in smaller local lakes and rivers and the more northern Great Lakes as temperature increases. Less habitat for cold water fish like lake trout. Reduced yields in certain crops such as corn. And all of this is an increased risk to human health. Also think about the wildfires up in Canada. Definitely a result of less precipitation and drier environments up there. That's releasing particulates as far as ash and other carbon particulates from the burning. And that's affecting air quality in the US, and we can only expect that that's going to increase. So not the most cheery of lectures, but It's a fact. Global climate has changed over the geologic history, so hopefully I showed you some ways that we measure that and have calculated that. But also, we can see very, very clearly that there's been a huge ramp up and increase in climate change as a result of global warming, and that's only going to affect the planet in the decades and maybe even centuries to come. So hopefully this is getting your wheels turning as to how we could maybe be a more positive force in the world as a result of climate change. And it's a giant problem. I'm not reinventing the wheel here by saying that. And so we have a lot of work to do as a species. So thank you very much for sitting through this, and hopefully you got a lot out of it. And yeah, see you next time.